Hi, how are you? I hope you are all doing fine. Today's topic is regression analysis. This is one of the most important topics in this class. So let's open the PowerPoint slide set. Okay. The slide set title is 3A Model Test. Okay, so standardized slopes and slope and model tests in simple linear regression. So today's topic is particularly simple regression, which has only one single predictor. Today's class is very focused on the conceptual explanation, so I really advise you to print this slide set and then make some notes when I explain the important concepts, please. Okay. This is a little bit higher. Okay. Okay. So page 2 looks like kind of outline of the today's lesson. So first one is estimate the model. Here we get the values of B0 and B1 plus other indices we saw last week. So B0 is y-intercept. B1 is slope. Other indices we saw last week. MSE, mean square error. MSE is the standard error of estimate. Do you remember that? And also standardized slopes. Okay, so we will learn that today, standardized slopes. Standardized slopes is also called beta weight. Second bullet is test overall relationship using F-test. Yeah, so overall relationship, overall model summary, overall test, omnibus test. This is for model summary, model quality. At that time we use R square. Do you remember that? As well as R square, we also use test value, which is F-test. So when we evaluate our model, whether or not our model is good or bad, we use the R square, but we also need to do statistical test. The R square is okay. So at that time we use F-test. You remember that? The last bullet is if overall relationship is significant. So that means if F-test is statistically significant, we move on the second stage, which is individual slope test, p-test. So continue with the description of effects of individual axes. So usually we have multiple X predictors, right? But today we have just one single X variable because we still need to learn like concepts used in regression. So t-test is gonna be the same as f-test because we have only one single X predictor. But after today, we will, talk about multiple regression. At that time, t-test is not gonna the same as the f-test because we have a multiple X variables, so we have a multiple slope tests. So far, we have only one X. So the test of beta 1 equals 0, the t-test. So single slope test is called t-test. Model test is called f-test. Okay. So we'll give the same decision as the overall f-test because in the single variable regression, we have only one single variable. So t-test result is gonna be the same as f-test result. But as I said, generally speaking, t-test is not gonna be the same as the f-test. Okay. Page 3. While in practice, we will test the overall model quality before testing individual slopes. Yes. We want to know the f-test first. The overall model is good or bad. So if the model is not good, then we don't need to even move on the second stage individual slope test. Okay. So in the parentheses here, null hypothesis test, beta 1 equals 0. This is a typical null hypothesis for individual slope test. Beta 1 is the individual slope in the population. Okay. Whenever you see Greek letter, that is a parameter in the population. And when you see just the alphabetical value like B1, B0, this is just statistics. And this is a parameter. Parameters are unknown value in the population because we don't collect population. However, we use this null hypothesis in the population. So later, we will learn about test of significance of the overall relationship. So what is the overall relationship? So do you remember the regression line? So the regression line is one best fitting line, one best regression estimation, right? So here, the test of significance of the overall relationship means the relationship between our observed y and y hat. Y hat is estimated line, regression line. So the relationship between observed values and estimated line. What is it? That is a rho square. So rho square, rho is a Greek letter of R. R is Pearson correlation, R relationship in the sample. But rho is relationship in the R. Now you see rho square. This is a model summary index. Okay, so null hypothesis, rho square equals 0. So this rho square between what and what? Observed values and y hat, regression line. Okay, so what is this meaning? If the relationship is good, the value wouldn't be 0, right? So if the relationship exists, we want to reject this null hypothesis. Null hypothesis says that relationship doesn't exist. Does it make sense? So the model summary, overall model test says the relationship is 0 or 0 here. And if we find enough evidence to reject this null hypothesis, then we say it's statistically significant. So sometimes it is statistically significant, or sometimes it is not statistically significant. So we need to have a criterion. When do we say it's statistically significant or not, right? We will talk about the criterion a little bit later. Anyway, this shows overall test, or we call it omnibus test, the model test. So our R square generated based on the sample analysis is acceptable. So we set up this in the population. This is Greek letter is parameters. So we always use Greek letters for the null hypothesis. Okay. Why do we do that then? Okay. So last time I briefly talked about the CLT, right? Central limit theorem. So let's say we have a jar, have 10,000 moles here. And if you have 100 researchers, theoretically speaking, you have 100 different samples out of the jar, right? Population. So you have 100 sample mean. And then each sample mean has, variation, deviation from the population mean. What do you call it? That's the variation, that is the sampling distribution, right? That is the sampling distribution. So since there is a deviation, we use the concept standard error of the sampling distribution, right? So here, your sample is only an estimate. Estimate means calculated value. Okay? So sample mean is the estimator of population mean. Likewise, other researcher has other sample mean. Likewise, the third researcher has other sample mean too. So we want to see this estimate, each estimate is trustworthy. Okay. Anyway, so here is an example of population. So a study of all college students in Maryland, and one sample, college students at UB. There are many universities, but let's say you just select just one cluster for the population, which is the UB students here. So think about it. If UB students are representative of the entire college students in Maryland. Okay. And another example, population, a study of all voters in a presidential election, all voters in the Southeast. What do you think about it? Do you think UB students or Southeast voters are representative to this population, respectively? So I'm talking about sample is supposed to be representative. Okay, it shouldn't be systemically, biased. So data collection is a kind of more important than data analysis. But this class is not about the sampling class, but about the statistics class. So, I can teach the sampling also because this course is analytical techniques, but I kind of assume the sampling is already representative. So then I can focus on techniques, especially regression. Okay, so there are so many things to learn. Okay, page 5. Population, the set of all individuals for whom you would ideally like to have, for example, all US citizens or all federal employees. Parameter is a number describing a characteristic of the population. So parameter is a true value. We never know the true value because we do not use population, because we do not have the population data. Maybe if we use the census data, still we have to have a sample from the census data. And sample is a subset of population. If the sample is chosen randomly, it is probably similar to the population. Statistic is a number describing a characteristic of a sample. Okay, so this sample belongs to the population. Does the sample provide convincing evidence that the two variables are related, not just in the sample, but also in population as a whole? So I believe you already learned this concept in PUAD 628. So I just want to quickly review this before we actually interpret the statistics shown in the simple regression. Okay, so why do we use a p-value? Why do we do a hypothesis test? What's the difference between mathematics and statistics? Yeah, okay. So logic of hypothesis testing. So for example, there are numerous tests, but in this case, let's say chi-square test. Especially chi-square test is when you want to see that whether or not if there is a difference between two categorical outcomes. Two categorical outcomes, you use chi-square test. For example, like gender. This is a categorical variable, not continuous variable, right? Also, racial ethnicity groups. It's also a categorical variable. So when you see, if there are any differences among the categorical subgroups, you use chi-square test. So let's read this one. We want to test whether the relationships that we see in the sample exist in the population. Researchers can develop two types of hypotheses. Okay, null hypothesis. There is no relationship between variable A and variable B. Researchers' hypothesis or alternative hypothesis. There is a relationship between two variables. So what we're gonna do here is we are interested in whether or not we reject the null hypothesis. So when you do not have enough evidence to see the null hypothesis is true, then you say you reject the null hypothesis, and then we call that it is statistically significant, right? Okay, so researchers' hypothesis is it's directional hypothesis, and then we do not try to reject or accept this researcher's hypothesis. So statistically, we use a null hypothesis, and then if we have enough evidence to reject the null hypothesis, then indirectly you can argue, oh, researchers' hypothesis is kind of okay for this moment. But later, if you have a more data added, then the result or your claim can be different, can be changed. Anyway, statistically, you use a null hypothesis, and then you want to see, or you want to say you're gonna reject the null hypothesis, or you fail to reject the null hypothesis. Okay. But in the research paper, actually, you use researcher's hypothesis. Whenever you post the hypothesis, you use researcher's hypothesis in your paper. But actually, when you use SPSS, and then when you do hypothesis testing, you use null hypothesis, and then your interest is only whether or not you can reject the null hypothesis. Okay, page 7. So interpreting the importance of slopes. So here we have to distinguish two different concepts. One, statistical significance. Two, practical importance. So statistical significance is the slope is statistically significant at the criterion value. So we call the criterion value is alpha. Usually we use 0.05. So if your p-value, probability value is larger than 0.05, and that means your null hypothesis is seen and more than 0.05, which means higher than 5%. So it's hard to reject that null hypothesis in that case. But if your p-value is smaller than probability value 0.05, then the occurrence of the null hypothesis situation in the population is smaller than 5%. So, we have like 95% confidence to say you reject the null hypothesis. That's fine. But if you have a higher than 0.05 alpha, then it's hard to say the null hypothesis is rejected. Does it make sense? Okay, I'm gonna repeat this again and again so you won't be confused later. Okay, but this is just the statistical significance. So here, red font, practical importance. This meaning is different from statistical significance. Okay, so let me use this example. Let's say one scientist invented like very good medicine to lose weight, and the medicine actually was effective in terms of the statistical significance. So the p-value was smaller than 0.05. So statistically significant. However, let's say that the medicine let us lose weight like 0.01 gram, even though you take the medicine like a lot, like 100 tablets. Then 100 tablets, wow, it's very painful, right? So practically speaking, the medicine is not that important, even though it's statistically significant. Does it make sense? So we need to distinguish two concepts, the statistical significance and the practical importance. So the first step is you see the p-value. Second step is you have to calculate the practical importance. We call that effect size. So if that has a high practical importance, then the effect size is high. So we're gonna touch that concept later. Also, the third paragraph, you may do this when comparing two different models or two different x variables. And in multiple regression, we will eventually want to choose among the predictors in one model to identify the most important x variable. So let's say we have two x variables in the one model, then you want to say which one is more important than the other on the y outcome. How can we do that? First of all, two x variables wouldn't have the same unit, same scale. Like for example, you know, let's say, how can I say, oh yeah, last week I was talking about the weight and height, right? So weight and height are, they use different units, right? Pound, right? And feet, they're different. So they cannot be comparable with the raw scale, right? However, we can make them standardized, and then they can be comparable magnitudes. Okay, so that standardized slopes can be used as effect size, which effect is higher than the other. Oh yeah, here, standardized regression equation. So when you have just the raw scale, X unit, X1 unit, X2 unit, they have different scales. You don't compare them because they use different scales, okay, weight and height. However, we can compare them when we standardize them. Mother summary, coefficient of determination R square. Okay, so strength of the regression model. So since the R, Pearson correlation, the maximum is 1, minimum is 0, absolute value. So between 0 and 1, since we know the highest value and lowest value in R, R square is kind of has the, you know, lowest value and highest value, which is 0 and 1 respectively. So you can compare the magnitude of this model and the magnitude of that model. Strength of the relationship between dependent variable and independent variable. So regression coefficient, this is unstandardized coefficient, slope, not standardized, so this is not comparable. Standardized coefficient is called beta weight. Beta weight. Correlation is also standardized covariance. So we have covariance. We learned that covariance can be standardized into correlation. Okay. Okay. So what we can understand is, what we should know is R squared, the concept of R squared is, so how well all of the model with the independent variable is working to predict the dependent variable. So if your model is good, your R squared is good. Here, beta weight is individual slopes goodness. So how well independent variable is pulling its weight to predict the dependent variable. So how well, how good the individual slope is, you can tell that through this beta weight. Beta weight or standardized coefficient is the average amount by which the dependent variable increases when the independent variable increases one standard deviation controlling for all other x variables. Do you remember the concept of the slope, just raw slope V1? I don't remember if I already talked about it, but so here beta weights concept how do we interpret that is when the independent variable increases 1 standard deviation. So here unit is 1 standard deviation. Then the amount of the change in y is also unit 1 standard deviation in y. So let's read the second one. When x changes by 1 standard deviation, and then y dv, dependent variable, changes by beta weight standard deviation. How can we convert this concept in unstandardized coefficient interpretation? So at that time, how do you do that? So if 1 unit changes in x, the amount of the B1 changes in y. This is the way how we interpret unstandardized coefficient, right? B1. But in this slide set, beta weight. So B star 1. Beta weight, how can we interpret it? Is when x changes by 1 standard deviation instead of just 1 unit. And then the y hat changes by beta weight B1 star standard deviation. Can you remember that? And if you have more than one x variable, you have to put this expression, holding the other variables in the mother constant. This means controlling for all other variables, all other x variables. Okay, now you remember this, right? We already covered this in PUAD 628. So you can revisit the PUAD 628 video. Interpreting the importance of slopes, we say the standardized slopes B star, B1 star, is the predicted number of standard deviations of change in y for 1 standard deviation unit increase in x. For example, so beta weight is equal to 0.75. We predict that y will increase by 0.75 of ASD, standard deviation, when x increases 1 SD. How do you know increase? Because this sign is positive. That's why. If B1 star is minus 0.75, you have to say like this, y will decrease by 0.75 of ASD when x increases 1 SD. Okay. In contrast, regression coefficients are expressed. Regression coefficient means unstandardized coefficients. Unstandardized coefficients are expressed in the unit of measurement of y hat, and the units may not be comparable. Years of service and gender, they are the two x variables, and salary is y dependent variable. But how can you compare the strengths between years and gender? Because they have different units. Interpreting the importance of slopes. To make the scales comparable, we compute a new score. So you have x variable, right? And you have x value, I individual x value, and you have x bar mean. And in order to standardize x, which is a z-score, you use subtraction, xi minus x bar, and denominator is standard deviation of x. Standard deviation of x. So these scores always have the mean zero, and variance 1. So if we do this for all the x's, the slopes computed based on those new z-scores will be comparable. So single predictor models, this gives us a very simple equation. So since we do not have y-intercept, because this is a z-score, z equation, B1 star is the so-called beta weight. Note the intercept is 0 because both zx and zy have the means of 0. We might also write the formula for the standard regression line. So here, this is individual value, z-score value. So we have error score. So this is a standardized residual. But if we have a regression line, this error is gone. Okay, estimated regression line has a hat. Zy hat, the predicted standardized score on yi for case I. B1 star, the beta weight or standardized coefficient, meaning the number of standard deviation of change predicted in y for one standard deviation increase in x. Zx, the standardized score on x for individual I. So B1 star equals Rxy. R is a Pearson correlation. B1 star is beta weight. I will explain this a little bit later because we do not know the original formula yet. So I want to explain the original formula first. Remember, this is only working well in simple regression. Yeah, here, this is not true when we get to the multiple regression context. I'll talk about it later. Jacob Cohen provided a set of values that have been used to represent sizes of correlation, mean differences, and a lot of other statistics. These came from evaluations of the power of tests, but they have been widely used in social sciences in other situations. So according to Cohen's rules of thumb, R or beta weight, the magnitude small 0.1, magnitude medium 0.3, magnitude large 0.5. So you multiply this, then you will get R square value. So if your model is higher than 0.25, it's regarded as a good model. Interpreting the importance of slopes. In our original SAT example, B1 star equals 0.65 SD of change is predicted in Y. So according to this slide set, we have two data sets, and the first one gives the slope 0.65, the second one gives 0.557. So this is stronger than the other. And second, the next one is here, NELS school data set. So I posted the NELS school data set in the Sakai site. And here, outcome variable is a sense of community, and independent variable is the teacher happiness. So these two columns for unstandardized coefficient. This is a regression coefficient, and standardized coefficient is 0.485. Unstandardized one is 0.75. So we do not know if this is big according to unstandardized coefficient, because every slope has a different units scale. But this is comparable because it is standardized. And this is test value and p-value. Okay, here sense of teacher community is outcome, and principal leadership is second predictor. And this unstandardized coefficient is smaller than this. But as I said before, we do not compare these two unstandardized coefficients each other. What we're gonna do is this standardized coefficient, because this is comparable. So the slope of principal leadership is 0.572, and the teacher happiness slope, beta weight, standardized slope is 0.485. So this is bigger than the other. So we think principal leadership is more important. This is effect size, comparable effect size. But you know, both of them, statistical significance shows what is the significance. P-value is smaller than 0.05. So in social science, mostly the criterion alpha value is decided as 0.05. So when we have a smaller p-value than 0.05, so the null hypothesis is rejected, because to see that kind of situation, like null hypothesis, wouldn't be shown very often. So that's why we reject the null hypothesis. Does it make sense? Anyway, we cannot distinguish which one is better than the other between two variables according to statistical significance, because both of them are statistically significant. However, when we compare the effect size and beta weight, we know principal leadership is practically more important than teacher happiness. So far, we have only one x, and then slope test is beta 1 equals 0. This is null hypothesis. And also this single hypothesis for single variable is the same as overall model test, because we have only one predictor, so it's going to be the same as the model test. However, we will have a different test if we have a multiple x variable. Okay. Hypothesis testing. So if null hypothesis is, about the slope is rejected, if p-value is smaller than 0.05, then we will interpret an effect size r squared b1, or the standardized slope b1 star. In other words, if p-value is not smaller than 0.05, we don't need to interpret b1 or beta weight b1 star. Hopefully you understand this kind of logic. So you see the model summary R squared. When does it when is it important? Only f-test p-value is statistically significant. Then you will bring the r-square. You will use the r-square. And then after the overall test is found out, statistically significant, and then you move on the second stage, individual slope test. Okay. Of course, this analysis are only used when assumptions are not violated, and assumptions are also very important. If assumptions are violated, your analysis is not trustworthy. So we're gonna learn assumptions later. Simplest hypothesis test using R-test, whether the correlation is 0 in the population. So the observed R came from a hypothetical null parameter, the probability. We want to determine the probability that are unobserved R. Sample statistic R came from a hypothetical null parameter. This is called rho. Rho is equal to 0. Sometimes this t statistic is squared, which results in a f statistic. And the degree of freedom, when we want to see the f test value, we need 2 degree of freedom. Okay, 1 and n minus 2 degrees of freedom. So 1 is predictor, number of predictor. Since we are doing this in the simple regression, 1, and then n minus 2, n is the sample size, n minus 2. So degree of freedom 1, degree of freedom 2. Okay, hypothesis testing for rho. Returning to the SAT and GPA example, our R was 0.65. We can test the null hypothesis that the correlation came from a population in which SAT and GPA are uncorrelated. Uncorrelated means the correlation equals 0. So that's why the rho equals 0. We can compare the t-value to a critical value in a t-table, or look up the p-value using SPSS or Excel. The 0.05 critical value, TF equals n minus 2 equals 28. So 2.048. This is when we have only one x variable in the model. So when you find out the test value, you use a distribution table. And distribution table gives the number 2.048. So you don't need to worry about that value because the textbook gives the table, or you can simply Google it.